Last time we started talking about why is or why might be that delta Q reversible divided by temperature be a state function. Why is it that when you give heat to a system reversibly, you know that the heat that you give to a system will depend on the path that you take. But if you divide by the temperature, which might be changing along that path, you get a state function. And this state function is called entropy, S. It is connected, it is the same as the molecular definition of entropy, Kb log W. We are not going to look at why they are exactly equivalent, like mathematically, but you can see intuitively why they might be equal, because increase in S corresponds to increase in heat given to a system, which is random motion increasing in the system. So intuitively you can see. But so what we did was to look at an ideal gas. We drew a pressure volume diagram. We had 2 points and we constructed 3 paths. And 2 of them I showed in class have the same change in entropy. One of them, many of you posted your practice solutions. I think that most of them are correct. I will post a solution later. I will probably also have that problem on the homework. So I really want everyone to go through it. So those of you who did the practice problem, I have 1 homework problem already done, which is great. So, but that was just an illustration that for an ideal gas, 3 different paths could lead to the same change in entropy. That is not a proof, right? What if there is some other path, even for an ideal gas, which has a different change in entropy? And how about a non-ideal gas? Is entropy still going to be a state function? And that's what we are going to do now. And the way we are going to do that is through the concept of something called a Carnot cycle. Carnot is named after some French, maybe Belgian, I don't know, physicist or engineer named Sadi Carnot, I think, who used to think about these things back in 200 years ago. So a Carnot cycle is a very special type of thermodynamic cycle. So this word cycle will keep coming up again and again. Cycle means that if you have some space, let's say you have some pressure volume space, and in this you start from some point and do something, and come back to that point. That's a cycle, right? Is this a cycle? The one in the bottom? It's also a cycle. It doesn't matter whether it looks like a circle or a square or a rectangle or a whatever, as long as you come back to the same point, it's a cycle. So a Carnot cycle is a very special type of cycle where you start from a certain point, you do an isothermal process that, let's say we started from a point A, we go to an isothermal process point B, through an isothermal process, we go through to a point B. Then we do an adiabatic process, which takes us to a point C. We do another isothermal process, which brings us to a point D. And then we do a final isothermal process, which takes us back to A. A final adiabatic process. So this, I will write it down once again. So we have A, B, isothermal, BC adiabatic, CD isothermal, DA adiabatic. This is it shown in a pressure volume diagram. So at this very point, I can tell you, in your exams and in your homeworks, you will be seeing future problems where I will ask you to take a process happening in a pressure volume diagram and convert it into some other diagram, convert it into a pressure temperature diagram, convert it into a pressure entropy diagram, right? And these type of things is something you will be doing again and again and again, which becomes very important. You can visualize one process in some other space as to what's happening. So, but this one is called an adiabatic process. It's an isothermal change followed by an adiabat, followed by another isothermal, followed by another adiabat, which brings it back to the same point. So our proof that entropy is really a state function for absolutely any material is going to be a 3-step process. This 3-step process will work as follows. And it's kind of an interesting proof as it builds up. The first one is to show that S is state function for Carnot cycle for ideal gas. So we want to show that for this particular cycle, integral of S around this cycle for an ideal gas is equal to 0, right? That is the same as proving it is a state function. You did whatever you did and you came back to where you are, entropy did not change. Clearly, that is not true for the heat taken by the system, right? You could do whatever you want, you come back there and you have taken some more heat. Entropy, we are going to show that if you move around this particular cycle, for this particular cycle, Carnot cycle, for a very special type of gas, an ideal gas, entropy change is 0, right? You kind of showed things like this in the diagram that we do last time. Remember, if you did the math over there, you would see the same thing. Like when you started from this point and did all of this and came back over here, the entropy change was 0. We are going to show that here for a different cycle, a very special cycle called a Carnot cycle. That's fine. That's not the full proof, right? Once we have shown this, we will use this to prove that actually Carnot is 0, not just for an ideal gas, but for anything. So on the top now, I have written anything. So first we will show that entropy along a cycle is 0 for an ideal gas along a Carnot cycle. Then we will remove this ideal gas assumption and show that it is actually true for not just an ideal gas, but for absolutely anything. And finally, after that, the third part is actually quite easy. We will show that indeed S as a cycle is equal to 0 for any cycle and any gas or any material. Okay, and that then proves, if you can show these 3 steps, and the way it will work is we will prove 1, use 1 to prove 2, prove 2, use 2 to prove 3. That's how it's going to work. Okay, and we will work through it systematically. Let's, and I'm not in a rush to finish this. We will go through as much as we can do today. We'll definitely finish it by the end of next class, by the beginning of next class. Most likely we can do the first part and the second part. The first part is easy. The second part is actually really easy, but trips a lot of students. It's like, wait, what? How could you do this? You will see. The second part is actually a lot of fun. That's the funnest part of the proof. But let's start with the first one. Okay. Any questions about this? Okay. So let me draw this cycle again. So part 1. So we want to prove that S is, the cycle of S is 0 along a Carnot cycle for an ideal gas. Okay, I hope that's clear. So maybe my handwriting has improved as I have gotten older, or you guys are just very kind. Which one is it? You're kind, right? Yeah, definitely kind. Okay, don't be that much. Okay, so let's try to do this. So let's draw our cycle. We have a pressure volume space in which we started from a point A. This isotherm took us over here. This adiabat took us over, isotherm took us to point B. The adiabat took us to point C. Another isotherm brought us back to point D. And then another adiabat took us to point A. Okay, so isotherm, adiabat. Let's call this as process 1, process 2, process 3, process 4. Okay, and what we want to do is to show that delta S is equal to delta S1 plus delta S2 plus delta S3 plus delta S4. What do we want to show? 0. Cool. Which one of these are definitely 0? So which ones? 2 and 4 are 0. Great, wonderful. And that is true even for a non-ideal gas. Here, it's true, it's an ideal gas, and we are doing all of this for ideal, okay? But it's definitely true for an ideal gas. It's true for anything. It's definitely true for an ideal gas. So we have to worry about delta S1 plus delta S3. So let's think about the processes in order to do this a bit more carefully. So one is a process that has isothermal, and by the way, every process here is reversible. I should have been very, very clear. All of these are reversible processes. We are not talking about irreversible processes, okay? Because our S is integral Q reversible, right? We are not talking about irreversibility yet. After this topic, we will move into irreversibility, which is actually very, very important. But for now, everything is reversible. So step one is isothermal reversible. Is it expansion or contraction? Huh? I want you all to be involved, or we will get totally lost, and it's not going to help anyone. You will become unhappy, then I will become unhappy, and together the world's unhappiness will increase. We don't want that, okay? Please stay with me, please participate, or it will become complicated. Is anyone who thinks that A to B is contraction and not expansion, or we can't say anything? It's expansion, right? You're going from volume here to volume here, and the volume axis is increasing. So this is isothermal reversible expansion. It's an isothermal process. It's a constant temperature process, right? So we can say this is happening at T is equal to T hot, some hot temperature, right? It's a hot, we will get to why we call it hot in a moment. But that's a process happening at some temperature, isothermal reversible expansion. So I had told you isothermal and reversible, but you can see it's also expansion happening at T is equal to TH. Let's say in this process, the system gains some heat, QH. Okay, it's an ideal gas, so expansion is not going to happen by losing heat, right? Expansion is going to happen by gaining heat. So QH must be positive, right? The system has gained some heat. Remember our first law of thermodynamics? Q was the heat given to the system, right? Now let's go to 2. This is adiabatic, reversible. Same thing. Is it contraction or expansion? Expansion once again, because I showed you, right? You're going to the right side. Great. Now comes the tricky question. What's going to happen to the temperature? Will it increase or decrease? Go ahead. Increase, are you sure? There are 2 answers. There are 3 answers, right? Who thinks it will increase? Okay. Who thinks it will decrease? Who thinks it will stay the same? Okay. Anyone who's okay, it's really split. Whoever thought it will increase, why do you think so? Let's work through it very systematically. You're all physical chemists, right? When in doubt, start with first law of thermodynamics. Delta U is equal to delta Q plus delta W. This is an adiabatic process. So what can we say here? Delta Q 0. Delta U is equal to delta W. Andrew's favorite relation. It's an ideal gas, right? So what can we say about delta U, Andrew? But first tell me what they want to say about delta U. It's okay, this is minus PdV, but on the left side, what can I say about this? Yeah, that's Andrew's favorite relation. Sit in the front, you will get a few theorems named after you. Okay, now who thinks the temperature will go up or down? Go ahead. Volume is expanding and you have a negative sign over here. So the temperature should go down, right? Temperature should go down. If dV is positive, dt is negative. So this one is a bit not so trivial, right? We had a, yeah, go ahead. Yeah, absolutely. You're correct. There are many ways of thinking about it, but this is one way. So this means that this goes from T is equal to T hot to some T is equal to T cold. That's why I called the upper one hot. Now it's clear that you're going down to a lower temperature, because if DV is, those of you who are watching the videos later, sorry, I wrote it on the blackboard. I'm not going to copy it on the iPad. Should come to class. So, okay, so this is expansion that took the system from a hot to a colder temperature. Now 3 and 4 should be easy. What is 3? Isothermal reversible contraction, right? And what's the temperature for 3 for this isothermal process? T cold. So those of you who came late, this stuff is tricky, okay? Please go through the video once again. I have also posted material. I know I'm not trying to guilt you into for coming late. Everyone has reasons for being late, and I hope you have valid reasons. But I have also posted video from Khan Academy on Carnot cycle. Go through it, okay? Carnot cycles are critical, and it's easy to get confused here. For example, certain of the arguments we used here they were easy now that you think through it, but they were not exactly trivial, right? You could not do it as you were listening to music, right? You would have to concentrate to get it right as to why is the temperature cooler at sea. So this is isothermal reversible contraction. So in this case, the system is going to lose some heat, right? Losing heat is the same as saying the system heat gains negative heat, right? We can do that. It's a bit bizarre way of saying that, but we can do that, right? It's the system gains some heat QC, but now QC is going to be negative. And 4 is once again adiabatic, reversible. In this case, it's contraction, right? And now we know that the temperature has to go from TC to TH. So we have described all 4 of our processes. We know what's happening to the temperature. We know what's happening to the everything. I would have been so happy if I could split the screens here. But, that's terrible. Okay, any questions about this before we go further? Okay, now let's think about what did we want to do here? We wanted to get delta S1 plus delta S3. Can anyone directly tell me what's going to be delta S1 given the things we have written down? You don't need to do any maths. The answer is right there. It's an isothermal process, and I'm asking you the entropy change during the isothermal process in terms of QH and TH. Go ahead. Absolutely. QH divided by TH. What's your name? Nathan. So Nathan gave with great confidence the right answer. Delta S1 is equal to, sorry, QH by TH. Is this obvious to everyone? Why could we do this? Because entropy is an integral of delta Q reversible. Entropy is an integral. But the wonderful thing about isothermal processes is that the temperature can go outside, right? And I've already told you that the system gains net heat QH. So this just becomes QH divided by temperature. So calculating entropy change is trivial for adiabatic processes, right? It's just 0. And it's not that hard for an isothermal process also, because you just have to know the total heat that went into a system. Isochoric processes and isobaric processes, the entropy change is a bit harder. You have to think more. It's not that easy, right? You have to use equation of state. But now you can kind of see why these relations might be useful, right? You have a chemical reaction that's happening in an isobaric process, and you're like, I don't know what to do. I don't know the equation of state for this material that I'm doing, right? But you can say, wait, my entropy is a state function. I will, if I can just calculate the heat given to the system and change it, think about it in an isothermal process, So state function is wonderful because you have to manipulate them. If once we have proved entropy is a state function. So that's delta S1. How about delta S3? What's that going to be? Go ahead. How about the minus sign? I already took care of the minus sign in QC, right? I already said QC is negative. So that's why you are correct. It's QC over TC. So now we have let's call this equation 1, and let's call this equation 2. So I'm going to switch the page. If you haven't copied anything, please do that. You really don't need to copy much. I mean, everything is online. So of course, if you're copying, you're probably going to stay awake. When I was a PhD student in my statistical mechanics and thermodynamics class, I liked it a lot, but I did not take any notes. So invariably, I will fall asleep after 10 minutes. That was not good. So we have just shown that delta S is equal to delta S1 plus delta S2 plus delta S3 plus delta S4. And I will draw it here so you have a reference. Isotherm, media bag. Okay. Arrows matter because they show the direction. So we showed that delta S1, the top isotherm, is QH by TH, delta S2 is 0. Yeah, delta S3 is QC by TC, and delta S4 is 0. So we got something that is QH by TH plus QC by TC. When we started this class, what did we set out to prove? Anyone remembers, or we have lost? That delta S is 0, right? Can you show that from here? It's not that obvious. We still have work to do. So now we have to think about what is QH for an ideal gas, right? Remember, we are working with ideal gas, so our life is not that complicated. Isothermal process. Let's go back to first law of thermodynamics once again. Isothermal, what is QH for ideal gas? In process 1, which is isothermal. So that means delta U is equal to QH plus delta W. Isothermal process, ideal gas. What can we say here? Left-hand side is equal to 0, right? Would you have said this for a real gas? You are all wonderful people. If you don't say this for a real gas at the end of the semester, I would have claimed it's a good victory for me. So QH plus delta W. What can we say about delta W? Let's think about reversible change, okay, just to keep things simple. So we can say 0 is equal to delta Q that is given to this system minus PdV, right? So now we can calculate QH. QH is going to be the integral of delta Q, and I'm not writing reversible because I've already specified everything is reversible, which is equal to integral PdV. Now what should we do? Your hint is ideal gas. Perfect. Who said that? What's your name? Oh, yes. Sorry, I forgot. What next, Hannah? There we go. If we took NR, it wouldn't help that much. But why can we take NRT out? Absolutely correct. And what is T? What value? TH. Right? So this is TH. And this is TC. So this is going to be NRTH integral dV by V, going from some volume VA to volume VB. So this will be NRTH ln VB by VA. That's my value of QH. And let's call this one as equation 3. And let's call this one as equation 4. Okay. Just staring at equation 4, can anyone tell me what will be the value of QC? It's very similar. It's an isothermal process. in an opposite direction at a lower temperature. So I'm not going to do the math again. I just want the answer. Go ahead. VA, VB, are you sure? This is going from DC to VD. Are you sure? VC over VD? There we go. It's very important. Why did you say VD over VC? You are trying to draw parallels, right? In the first one, you had temperature multiplied by log of final volume by initial volume. Here also, you will do temperature multiplied by final volume by initial volume, right? And if you don't like how I just wrote this down, you can go through the full thing we did for equation 4 and come to the same conclusion, but it's just the same thing. So now let's put 4 and 5 in 3. Let's see if we get our answer. Unfortunately, we won't. We still have some work left. QH by TH. What is QH by TH? That is NR ln VB by VA, right? QC by TC. QC by TC is NR ln VD by VC. So this thing becomes NR ln, due to the wonderful properties of log, VB by VA multiplied by VD by VC. Is that going to be 0? Go ahead. Oh, because I divided in this one. It's really nice how it drops out, right? It just drops out. It's almost magic. Is everyone happy with why I removed the temperature? If you're unhappy, I'll go back. Okay. So we got an expression that says delta S is equal to NR ln this volume multiplied by this volume divided by this volume multiplied by this volume. Kind of see. So when will delta S be 0? When those volumes, that thing in the square bracket becomes 1, right? Then it will be 0. So we want to show that the product of, I should write it down, this is VB, and this is VD. We want to show that product of VB multiplied by VD is the same as the product of VA multiplied by VC. You can kind of see why it might be same, but kind of doesn't do it, right? You will get one point in the exam if you say kind of looks like it. We have to prove it. How do we do that? Any ideas? Go ahead. VD equal VA. Yeah, because it's a product. So but VD is not equal to VA. It's a contraction. VD equal to VA would mean this is a square or a rectangle. It's not a rectangle. The thing is slanted. The thing is slanted. Life is a bit complicated. It's not that easy. Go ahead, JP.
You have to use your ideal gas relations to show that VD over VC equals VD over VA with the volume pressure relation.
Will that do it though? Go ahead.
Assume like temperature values and then solve through ideal gas law, or you might be able to work through the adiabatics.
So the way I'm going to do it is to go through the adiabatic. So, and what you said, what the others said, it might be a way out, but I don't know. This way at least will get you to the right answer. So note down this expression and look at that picture, and then we are going to switch pages here and work through what happens. So let me draw this once again here. We had this isotherm. We had an adiabat, iso, adia, iso, adia, and then a pressure volume thing. Okay. Let's focus on this one. This process 4. At the top over here, we have what is the volume, VA, and what is the temperature at the top? TH, right? What is the volume at the bottom? VD. What is the temperature? TC. Did we derive anything about how volume and temperature change during an adiabatic process for an ideal gas? We have seen it. You all even saw it in the midterm in a related form. Remember? Yeah, everyone remembers the expression? There is a power, right? It was something like Vt to the power k is equal to constant. I don't really care what is the power here. I'm just going to call it, let's not call it k, because then you will be like, oh, that's Boltzmann constant. Let's not do it. What should we call it? Let's call it xi. Okay, some squiggly thing. Xi, I claim. I don't care what is that thing. Okay, it's some constant which depends on the heat capacity and the degrees of freedom and all those wonderful things. What does this mean for us? VA TH to the power Ziegler is equal to VD TC to the power Ziegler. Correct? Now let's go and look at this adiabat over here, the other one on the right side. Ugh. What is the temperature? What is the volume on top here? VB. And what is the temperature? TH. How about here? What is the volume? VC. And what is the temperature? TC. Can I write down a similar relation for this other adiabat? Who said sure? Marco, go ahead. Tell me the relation. Okay. Now, do you see how that equation 5 might come true? Equation 6 might help us, because if you divide both of these, let's call it 7a and 7b. If you divide them, what do you get? VA by VB multiplied by TH to the power Ziegler divided by TH to the power Ziegler is equal to VD by VC TC to the power Ziegler divided by TC to the power Ziegler. This just cancels out. This is just one both sides. Or VA by VB is equal to VD by VC. Or if you take VB over here, VB VD by VA VC is equal to 1. That is exactly what we had here, VB VD by VA VC. So this is equation 8. Put 8 in 6. Delta S is equal to 0. We proved it. Good job, everyone. Now, in order to prove that that thing inside the square bracket was 1, I went through this adiabatic path. You could have done it some other way. I invite you to go and try it. It's good practice for this class, just to see if you could have derived that relation some other way. Probably you could have. I won't be surprised. So what have we shown so far? We have shown that for a Carnot cycle, so this cycle over here is a very special cycle known as the Carnot cycle. We have shown that for a Carnot cycle, the entropy change along this cycle for an ideal gas is 0. This is not the full proof that entropy change along any cycle for any gas is 0. We have to work our way through it. But this brings me up to some more practice problems. How many? We have had 5, right? And I will be posting solutions, but I want to see more attempts. So practice problem 6 has many parts. Draw Carnot cycle in PT diagram, in PS diagram, pressure entropy, and what else? In VT diagram. Try to draw it in all 3 and see how it looks. This is really, really good practice. I cannot tell you how, if you can do this confidently, you're in very, very good shape for this. You're looking at an A in this class if you can do this confidently. without any doubts. It's not easy to do this. Work through this. And if you feel like, oh, this was easy, then you are in very good shape. If it does not feel easy, don't give up hope. You can still get into good shape, but it will be a good test for you. Okay, so please work through drawing the Carnot cycle in all three of these. Okay, so our agenda for today's class was to show, it was a three-step agenda. First was to show that S is a state function for Carnot cycle for an ideal gas, which means along a cycle, if you calculate S, it is 0. It doesn't matter that you did all those complicated things, you came back, you found the entropy to be the same. And think, here we are drawing things on a blackboard or on an iPad screen, but those are complicated things that are going on, right? You're constructing complicated machinery to do everything, but yet you come back, and if it was an ideal gas, entropy would be the same. That's what we have shown. Now we have to show that this is true not just for an ideal gas, but for any gas. A Carnot cycle, if you were working even on a real gas, which is something you can actually do, if you actually implemented a Carnot cycle and you came back to the same point, the entropy is going to be the same. Okay, so before I move on to that, any questions about this part? No questions about this? Okay. So now we are moving to step 2, which is to show Carnot cycle, any substance, real, ideal, van der Waal, whatever. You are going to get delta S along a cycle equal to 0. How do we do that? This proof, like I said, is the most interesting. It's a bit different. It's something, unless you have read it in a textbook how to do this, you'd probably not be able to think of it on your own. It's complicated. It's simple once you look at it and understand it, but it's not something you could have just imagined it on your own. It's a bit, for those of you who like geometry, you know, sometimes when you have to prove theorems in geometry and the only way to do it is to construct a random line somewhere and show that, if you know what I'm talking about, and those proofs are like, how could you have thought to construct this line over here? This is that kind of a proof. So when you look at it, hopefully you will agree that it's simple, but I could not have thought of this proof on my own. So in order to prove this, we are going to introduce a concept which we talked about when we started with heat and work and things like that, which is the concept of efficiency of a thermodynamic engine. This efficiency has the symbol eta. And we talked about efficiency when we talked about Kelvin's statement of second law of thermodynamics, right? We said that we have a hot source. Oh, by the way, yesterday I was visiting Carnegie Mellon University to give a seminar, and I met a student who is working in their molecular biophysics PhD program. His name is Matt Martin. He was an undergrad here, and he took 481 with Amy Mullin, and he tells me that he went through our math modules. That was pretty good. And he said he learned a lot of math from that. So, you know, I felt very proud. Just thought I would share. So you have efficiency of a thermodynamic engine. How do we define this? We have a hot source. Now he's working on cryo-electron microscopy, which is not very hot. It's very cold. And you are taking heat from a hot source. And this heat is being used to turn some kind of motor, which does work. And what did Kelvin's statement of second law tell us? You must be losing some heat to a cold sink, right? You cannot just be like 100% efficient in converting all your food into energy, for example. You must have some dissipation going on into a cold sink. And this work is W. So you can define the efficiency as, and I'm going to use modulus just to avoid confusions with signs and things like that. This is the ratio of the modulus of the work performed out of it divided by the heat absorbed. So it's a modulus. Both things are absolute values. So what is the minimum value eta can take? 0. It cannot be smaller than 0, right? Everything is positive here. You cannot have a negative number. So eta is larger than 0. What is the largest value eta can take? 1. Can eta be more than 1? That would be very strange, right? You took some heat and you did more work than that, right? That would be like Bitcoin. You put some money and you think you will become very, very rich. It doesn't happen. Go ahead. Yeah, sure. Yeah, I'm casual about that. So how do we write the modulus of the work done in terms of modulus of the heat and modulus of these two things? How do we express work in terms of these two? What is the relation? Go ahead. QH minus QC, right? So because QC is not going to be more than QH, the modulus. You cannot be dumping more heat than you got from the original sink. It's going to be very strange, right? So work is the ratio, is the difference between these two. So if we think about this equation, which is equation number 9 and equation number 10, we can write down eta in terms of purely QH and QC as work performed, which is modulus of QH minus modulus of QC divided by heat absorbed, which is QH. So this is equal to 1 minus QC by QH. Now happens something interesting. When we worked through that, we actually did calculate QC and QH for a Carnot cycle, right? What was the value of QC by QH for a Carnot cycle? It seems to involve all those ugly volumes. But the volumes cancel out. The volumes. Or we don't even have to go to that. We just showed, if you think about this thing, we showed that delta S is equal to 0, right? What does that tell us about the modulus of QH divided by modulus of QC? What does this tell us about QH by QC? That this is equal to 0, which we showed. This is important that we get it right. Everyone should be on the same page. Anyone from this side? I feel like you guys, I'm losing you. What's your name? With the big M. Yeah? Sarah, what do you think? What will be QH by QC? That whole thing over here, let me help you. This thing is 0. Let's work through it. So QH by TH plus QC by TC is equal to 0, right? So can I write it as QH by TH is equal to minus QC by TC? Are you happy with that? Sarah? Okay, tell me when you're unhappy, okay? Now if I put a modulus sign, I can get rid of this minus, right? Because it's a modulus sign, I'm thinking of absolute value, QC by TC. Now can I say something about QH by QC? In terms of the temperature? If I bring this over here, I could take this temperature over here, right? So would you agree, Sarah, that QH by QC is equal to TH by TC? You seem unhappy. It's because I put you on this spot, I'm sorry. But think about it, okay? And if it's not clear at home, let me know. This is important, that QH by QC is TH by TC for a Carnot cycle. Okay? Are most people happy with it? Is someone unhappy with it? You're unhappy. Go ahead.
Wait, so you use that from the fact that delta is 0, right?
Yeah.
But that's only for ideal gas.
Yeah.
So you can't apply for real gas.
No, I'm just saying for an ideal gas. Yeah. This is true only for an ideal gas, this whole business. So yeah, let me write it down. So we showed that eta, therefore eta is equal to 1 minus Tc by Th for an ideal gas, right? So this is another way of saying that if you have a Carnot cycle working for an ideal gas between cold sink Tc and hot source Th, the efficiency of that Carnot cycle will be 1 minus Tc by Th. Okay, so if you want to make a Carnot cycle for an ideal gas very, 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 very efficient, what should you do to the cold source, a cold sink? Make it as cold as possible, right? The efficiency will go to 1, or start drawing energy from something as hot as possible, and the efficiency goes to 1, which is kind of peculiar. I will post an article later where you can see how you can model hurricanes as a Carnot cycle, how they are drawing energy from the ocean and give it in somewhere else. And it's interesting how it plays up in various forms of nature. But this is only for an ideal gas, as you pointed out. We are not done yet. The point though is, if we could show that indeed this efficiency is true, not just for an ideal gas Carnot cycle, but any gas Carnot cycle, then we are done. Then we have proved what we want to prove. And let's work through that. So first, let's just show. Let's prove that eta, the efficiency, is equal to 1 minus Tc by Th is true for any gas on a Carnot cycle. If we could show this, and then we go back to this Carnot cycle for any gas, this directly implies, this would imply delta S Carnot is equal to 0 for any gas. Why? Let's work through it again. For any gas, delta S Carnot is delta S1 plus delta S2 plus delta S3 plus delta S4. Now it's no longer an ideal gas. Can we still say delta S3 is 0? No, delta S2 is 0. For any gas, you're nodding your head, you don't like it? It's an adiabatic. So it could be ideal or non-ideal, doesn't matter. Delta S2 is 0 for any gas. If it's an adiabatic process, delta S2 is 0, right? That's the wonderful thing. So this would be 0, and this would be 0. Delta S4 would also be 0. What is delta S1? That is again going to be QH by TH. And delta S3 will be QC by TC. This thing applies for any gas, not just an ideal gas. Remember why they argue? How did we get there? Hannah said that we have this thing and the temperature can be drawn out, right? That we can draw out the temperature for an isothermal process. That has nothing to do whether this is an ideal gas or a non-ideal gas, right? We are not using equation of state. We are just drawing out the temperature. So delta S Carnot is equal to QH by TH plus QC by TC for any gas. And if we could show that eta is equal to 1 minus TC by TH, where eta is indeed defined as 1 minus QC by QH, right? Then we have shown that this thing is 0 for any gas. This is the proof. Like I said, the part 2 is the most complicated. It takes time to work through it. Once you have understood it, you will be like, okay, this was easy. But working through it, it's a bit convoluted almost. It's like, wait, why did we define this? Why did we do that? If we could show that eta, and I'm going to finish here and we'll work. Next time I will start from the beginning of step 2 again because it's complicated. So if you could show that 1 minus QC by QH, that is the definition of eta, is equal to 1 minus TC by TH, then we have shown that QC by QH is equal to TC by TH. Therefore, and we know what are the signs of our QH and QC, so we are okay in doing this. Therefore, QH by TH plus QC by TC is equal to 0. Therefore, delta S Carnot any gas is equal to 0. So the point now remains is to show that the efficiency is equal to 1 minus Tc by Th, not just for a ideal gas, but for any gas. And next time we are going to do this, and the way we are going to do this is quite interesting. We will do it through contradiction. We will imagine, let's imagine there is an engine where the efficiency can be higher than this. We will run one engine forward, we will run one engine backward, and we will show that we get to a violation of second law of thermodynamics. So we will do this next time, and I will start again from the beginning of step 2. I am ready to bet that a third of you are probably confused in this, because at least a third, this is confusing. Please go through my notes, please go through Atkins again, and we will work through this again next time.